So now let's talk about relationships formed by tangents and circumscribed angles. So a tangent is just a line that intersects a circle at exactly one point. So here's an example of a tangent. See how it only touches a circle right here at point P? That's the only spot. That's what makes that a tangent. We call point P the point of tangency. So that's our point of tangency, and PQ is a tangent. And again, a tangent is just a line that touches a circle at exactly one point. Let's talk a little bit about circumscribed angles. Before we talked about inscribed angles, they had their vertex on the circle. Notice that a circumscribed angle has the vertex outside of the circle. A circumscribed angle is actually formed by two rays that have a common endpoint that are tangent to the circle. So both of these rays touch the circle at exactly one point, and they have a common endpoint. And that endpoint is outside of the circle. So here are some ways that we can use tangents and circumscribed angles. One thing that we know is that if a line is tangent to its circle, then it's perpendicular to the radius drawn to the point of tangency. Try it out for yourself. Draw a circle, and then draw a tangent line to that circle that touches it at just one point, and then draw a radius that intersects with that tangent. Start by drawing the center of your circle, and then just draw a path to the tangent. However you draw it, that radius is going to be perpendicular to the tangent line, and that's what that theorem is saying. And here's an example of where that would be useful. Here we have a triangle, and I see that we have a radius of the circle here, and we also have a tangent. I know one of my angle measures. Could I figure out the others? Well, sure I could, because I know this is actually a right triangle, because it's formed by a radius that intersects a tangent line at the point of tangency. So I have 46 degrees, I have 90 degrees, and I could just use the interior angles of a triangle to figure out my final angle over here. So that angle would be 44 degrees. We also talked a little bit about circumscribed angles. So when would we use those? Well, the circumscribed angle theorem tells us that a circumscribed angle of a circle and its associated central angle are supplementary. In other words, angle D and angle B are supplementary. They add up to 180. So that's pretty useful. For example, in this circle over here, we have 144 and we have an angle measure that we don't know, but we know that these two add to 180. So we can just subtract 144 from 180 to figure out our missing angle. And we can tell that our missing angle is going to be 36 degrees. So now that we've seen some examples of how tangents and circumscribed angles are useful, work with me a little bit here on a proof. So what we want to prove here is that NO is congruent to PO, and they are congruent. In fact, they always will be. And we're going to prove that it's true. Here's our first step. Our first step is to draw a line segment MO. So go ahead and draw that. And then we want to prove that we have two congruent triangles. I'm going to erase my original tick marks because that's what we're trying to prove. We don't actually know that's the case yet, but I'm going to put a tick mark right here on MO because we know that MO is congruent to itself by the reflexive property of congruence. We also know that MN is congruent to MP because they are both radiuses of circles, and all radiuses of a circle are congruent. So going back to our triangle congruence proofs here, we have a hypotenuse and we have a leg for each of these triangles, and they are right triangles. So we can use hypotenuse leg congruence to show that these two triangles are congruent to each other. And since the triangles are congruent, all of the corresponding parts of the triangles are congruent. So we'd say corresponding parts of congruent triangles are congruent, and that is sufficient to tell us that NO is congruent to PO. So in other words, tangents to a circle that have a common endpoint are congruent.